Hello everyone, my name is Santosh and I am a student of BSc Chemistry Honours first year. It is a presentation video on alkyl halides and some important reactions. Alkyl halides, compounds which are formed by replacement of hydrogen atom of alkanes, RH give rise to RX by adding X and removing H. Types: primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. Primary alkyl halides which have no R group. Secondary alkyl halides 2 R groups means 2 plus I groups. Tertiary alkyl halides 3 R groups present on the carbon atom having X group means 3 plus I groups. 3 bulky groups create steric hindrance. Alkyl halides show nucleophilic substitution reactions. Halogens are more electronegative than the carbon. Carbon atoms acquires S plus charge, partially positive charge, and halogen acquire partially negative charge. Due to this, the nucleophile will attack on the central atom. Hence, alkyl halide will show nucleophilic reaction. Carbon can make only 4 bonds as it is tetravalent. Due to the presence of single bond between carbon atom and the X atom, halogen atom will be removed and due to this, the alkyl halide will show the nucleophilic substitution reaction. They can also show the elimination reaction. CH3CH3CH3Cl in the presence of alcoholic KOH give rise to CH3CH3CH3O negative, K positive, not a nucleophile but have a bulky group, cannot approach the carbon atom to reactant due to the steric hindrance, and it will attack on the hydrogen atom, will behave as a base. If 2 hydrogen of carbon atom are replaced by R groups. Potassium tertiary butoxide, it will give rise to CH3 double bond CH2. The reaction in which 2 atoms or groups of atoms are lost either from the same or the adjacent carbon atoms are known as the elimination reactions. Types of nucleophilic substitution reactions: the SN1 reaction, unimolecular nucleophilic substitution reaction, and SN2 reaction, the nucleophilic substitution bimolecular reaction. Elimination reactions: 2 atoms or groups of atoms either from the same or the adjacent carbon atoms. Types: the alpha elimination and the beta elimination. Beta elimination E1, E2 and E1CB. The E2 elimination. The mechanism involves a single step bimolecular elimination process. The attacking base removes a proton from a beta carbon with the simultaneous loss of halide from the alpha carbon and the formation of an additional product. Structural factors. For a given alkyl group, the rate of elimination varies with the nature of halogen in the order Ri, then Rbr, then Rcl, and then Rf in the decreasing order. The case of elimination, the ease of elimination follow the order tertiary halide, then secondary halide, and then primary halide. Unlike SN2 reactions, E2 reactions are not appreciably influenced by the steric factors and take place easily with the tertiary alkyl halides. Generally speaking, E2 elimination reactions tends to yield the most stable alkene, which usually the most substituted. Even mechanism. This mechanism operates through a two-step process in which the rate determining step involves only one molecule. In the first step, which is slow rate determining step, the alkyl halides dissociate into the carbocations. In the second step, carbocation loses a proton to the base and forms the alkenes. E1CB mechanism. E1CB mechanism is a reaction, and it is a two-step process that involves the removal of a proton and leaving group from the molecule, and this reaction occurs under basic condition and forms a double or a triple bond. Steps of E1CB. A base removes a proton from the beta carbon, forming a carbon ion intermediate, and the second one is the leaving group detached and a double bond forms. E1CB is a unimolecular reaction. SN1, the unimolecular nucleophilic substitution reaction. Reaction in which only one molecule is involved in the first step of reaction, the rate determining step of the reaction. Tertiary alkyl halide is involved so that the nucleophile cannot attack in the first step of reaction. Only one molecule will be involved. SN1 reaction. Due to the presence of the bulky groups, the nucleophile will not be able to approach the carbon atom. Nucleophile should be weak but large in size. The formation of carbocation takes place. Partial racemization takes place in more polar medium. Polar protic solvent is used as the proton donor. CCH3Cl plus AgKOH on heating give rise to CH3 thrice COH plus KCl. Two-step mechanism. Step first, the formation of the carbocation, the intermediate, which is a slow step. Transition state will form. The rate of reaction is directly proportional to the concentration of reactant. Molecularity 1, order 1. The step 2, attack of nucleophile. It is a fast step. Tertiary butyl alcohol is a major product and KCl will be the side product. When CH3 carbocation plus AgKOH will react. Transition state second will form. Due to the stability of carbocation, the order of reaction, rate of reaction will be tertiary, then secondary, then primary in the decreasing order. Bimolecular nucleophilic substitution reaction, the SN2 reaction. Reaction in which two molecules are involved in the rate determining step of the reaction. Primary alkyl halide is involved so that the nucleophile can attack in the first step of reaction. Two molecules will be involved in the SN2 reaction. Nucleophile can approach easily. Nucleophile should be strong but small. Formation of transition takes place. Walden inversion takes place in it takes place in the less polar medium. Polar aprotic solution is used. CH3CH2Cl plus aqueous KOH on heating will give rise to CH3CH2OH plus KCl. One step, concentrated mechanism. Attacking of OH negative group and leaving of chlorine negative takes place simultaneous because if Cl negative is removed first, then carbocation will be formed and will be less stable. Transition state, only one possibility of attack, which will be the back. The inversion of configuration takes place. No intermediate will be formed and the rate of reaction is inversely proportional to steric hindrance. So the rate of reaction will be primary, then secondary, then tertiary in decreasing order. Factors affecting SN2 reaction are the nature of the alkyl group in the alkyl halides, that is the steric factors, the nature of the nucleophilic agents, the nature of the halogen atoms in the alkyl halide, and the nature of the solvent. Factors affecting SN1 reaction: nature of alkyl halides the nature of alkyl in alkyl halides, nature of halogen atom in alkyl halides, nature of nucleophile reagent, and the nature of solvent. Vinyl halides are less reactive than the benzyl halides due to the difference in the stability of their reaction intermediates and the nature of their bonding structure and the resonance stabilizing. Benzyl halides have the halogen attached to the benzylic carbon. When undergoing nucleophilic substitution or the elimination, they form a benzylic carbocation which is highly stabilized by resonance with the aromatic ring. Vinyl halide has the halogen directly attached to the carbon-carbon double bond. The vinyl carbocation that would form during stabilization during substitution is extremely unstable because the positive charge would be on the sp2 hybridized carbon, which is less stable than a benzylic carbocation, and the p orbital involved in the double bond is not aligned properly to stabilize the carbocation through hyperconjugation or resonance with the halogen. Bond strength. In vinyl halides, the CH bond has partial double bond character due to the overlap between the p orbital of the halogen and the pi system of the double bond, making it stronger and harder to break. In benzyl halides, the carbon halogen bond is a regular single bond which is weaker and easier to break. Electron density. The electron-rich double bond in vinyl halides repels nucleophile, making nucleophile attacks less favorable. Benzyl halides don't have the repulsion and are more accessible to nucleophiles. How can you make the iodination reaction of benzene more forward or irreversible? By Add an oxidizing agent that removes Hi by oxidizing it to I2 or I positive. This drives the reaction forward by the Le-Chatelier's principle, and the oxidizing agents are HNO3, HiO3, CuCl2 or H2O2. We can also use of Lewis acid catalyst. Catalysts like FeCl3, AlCl3 or CuCl2 help in halogenation, but with iodine they are not very effective alone because I2 is too unreactive, so they are often combined with an oxidizer. Use of iodine monochloride. ICL is more reactive than I2 and gives better yields of iodobenzene, and ICL acts like an activated iodine source. Summary: to make iodination of benzene more forward, use the oxidizing agents, use ICL instead of I2, and optionally combine Lewis acids with the oxidizers. Thank you.